Hello, today I'm going to present our work entitled Synthesis and Luminescent Properties of Mononuclear Europium Complexes with Benzoate and Ibuprofen ligands for antenna effect optimization. This work focuses on the development of Europium coordination compounds with enhanced luminescent properties for potential optoelectronic applications such as phosphors, light emitting devices, optical sensors, and photoelectronic materials. Europium is the most attractive lanthanide ions because it exhibits red emission so intense, narrow emission bonds, excellent color purity, and long luminescence lifetimes. However, Europium absorbs light very inefficiently because its FF electronic transitions are partly forbidden. But to overcome this limitation, organic ligands are coordinated to the metal center. These ligands absorb ultraviolet radiation and transfer the absorbed energy to the europium ion through the antenna effect, significantly increasing its luminescence. Therefore, the selection of suitable ligands and the coordination environment are key factors for designing highly efficient luminescent materials. For this reason, in this work, we select benzoate and ibuprofenate ligands to investigate how different coordination environments affect the optical properties of europium complexes. The main objective of this work was to synthesize 4 mononuclear europium complexes using benzoate and ibuprofen ligands and evaluate how different coordination environments influence the antenna effect and the luminescent properties of europium. Now I will briefly describe the synthesis. The 4 europium complexes were synthesized using a two-step precipitation method. In the first step, 2 precursors complexes were prepared. The first precursor was synthesized by coordinating 3 benzoate ligands to a europium ion. Each benzoate ligand coordinates through its 2 oxygen atoms, contributes with 1 negative charge, and therefore 3 benzoate ligands are required to balance the 3 charge of europium ion, producing a neutral coordination compound. Following the same procedure, a second precursor was synthesized, and once both precursors complexes were obtained, the coordination sphere was modified by introducing a second ligand. 2 ibuprofen molecules were incorporated into the benzoate precursors, while 2 benzoic acid molecules were added to the ibuprofenate precursors, yielding the 4 coordination compounds presented in the figure 1. The use of 2 different ligands was intentionally selected because increasing the asymmetry around the europium coordination center has been reported to enhance electric dipole transition and improve ligands to metal energy transfer, leading to more efficient antenna effect. To verify that the ligands were successfully coordinated to europium, FTIR spectroscopy was performed. In both synthesis route, the characteristic asymmetric and symmetric stretching abbreviation of the carboxyl groups were observed. When comparing the precursor complexes with the final mixed ligand complex, slight shifts in these bonds indicate change in the coordination environment after the incorporation of the second ligand. This spectral change confirmed the successful formation of the mixed ligand europium coordination compounds. X-ray diffraction was used to evaluate the structural order of the synthesis of materials, as shown in the different diffraction patterns. All samples exhibit a broad diffuse adult center between approximately 20 and 30 degrees Celsius, and in addition, no sharp Bragg reflections are observed. The results indicate that all synthesized coordination compounds possess a predominantly amorphous structure. Now, according to the photoluminescent studios, excitation spectroscopy was used to evaluate the efficiency of the antenna effect. In this case, the precursor complexes exhibits broad absorption bonds in ultraviolet region from the organic ligands. After the incorporation of the second ligand, we have an increase in excitation intensity in both synthesis routes. This behavior indicates that modifying the coordination environment improves ligand to metal energy transfer, allowing more efficient sensitization from europium ion. Finally, for the photoluminescent studies, the luminescent properties were evaluated through emission spectroscopy. All synthesized compounds display the characteristic emission bonds of europium, dominated by the 5D0 to 7F2 transition responsible to the intense red emission. However, significant differences in emission intensity were observed among the synthesis complexes. The mixed ligand complex containing 3 benzoate ligands and 2 ibuprofen molecules exhibit the highest emission intensity. This result indicates that this coordination environment provides the most efficient antenna effect and the most effective energy transfer from the ligands to the europium ion. Overall, these results demonstrate that both ligand selection and coordination geometry is strongly influenced by the luminescent performance of Europium complexes. As a conclusion, we have that 4 mononuclear Europium complexes with different ligand environments were successfully synthesized. Also, FTIR confirmed the coordination of benzoate and ibuprofen ligands, while X-ray diffraction revealed that all synthesized compounds are predominantly amorphous. The incorporation of a second ligand enhanced both excitation and emission intensities, confirming that increasing the asymmetry around the Europium coordination center improves the antenna effect. Also, among the synthesis compounds, the mixed ligand complex containing 3 benzoate ligands and 2 ibuprofen molecules exhibited the highest luminescent intensity. And these findings demonstrate that ligand selection and coordination geometry are key parameters for designing highly efficient Europium-based luminescent materials with potential applications in photoelectronic devices. That's it. Thank you for your attention.